All right, it's the second to last week of class, and obviously I have a different setup today. And that's because I have a huge deadline tonight, and so I couldn't make slides. But another reason is that a lot of the material that I'm going to talk about in my research area, the things I like, is heavily mathematically related, and PowerPoint's not really a good tool for that. So that's what I'm going to do today, Wednesday, and Thursday. And next week is going to be all project stuff. So you guys are going to present what you've done in your projects, and that'll be really interesting. So another thing is that assignment 6 is due, and the second project interim report was also due this weekend. So any questions on assignment 6 or that?
And assignment 7 is due this week?
Yeah, assignment 7 is due when it says it's due. Kind of an existential point. It's due when it's due. Right. Yeah, so for assignment 6, I also posted a solution of that really hard extra credit question just in case if you're wondering how that was done. So I don't think anyone got it, but there were some creative answers about that. So any questions before we get back to this stuff? So obviously I sent the announcement about all the project-related information for how long you should talk, when all the due dates are. So any questions about any of that stuff? Okay. So we've been talking about these two classes of problems called P and NP. So P stands for polynomial time. Deterministic polynomial time. So I have some algorithm for a particular problem that when I take an instance of that problem, I can figure out whether it belongs to this problem or it says yes, essentially, to this problem in polynomial time in terms of the size of the input, or I say no in polynomial time. Then we also talked about this class called NP, which is nondeterministic poly time. We came up with those two formulations, which were about either we can deterministically verify a certificate, so this candidate solution, I can deterministically say whether that that certificate actually is a valid reasoning for why this instance belongs to this problem or it doesn't. So whether I should say yes or no in polytime. But we can also think of it in terms of nondeterminism. So we can think of that as a sequence of choices that are non-deterministic in nature. So non-deterministic means that if there is a way to eventually say yes, we will make the right choice, the right set of choices. And whatever right means in terms of a problem, set of choices. So as an example for an NP problem, like I'm given a graph and two vertices S and T, and I want to determine whether S is connected to T. And so obviously it's in polytime because of breadth first search, but we can think of this in terms of NP, in terms of the non-deterministic choice of vertices along the way. So if I have S over here, and I have T over here, I can say, I may have a lot of choices that I can make here, but if they really are connected, I will make a choice that will eventually get me to T. Right? So I will make this, for example, this edge. I will choose this edge with this vertex on the other side. And then I'll keep non-deterministically choosing until the non-determinism stops and I reach T, or it stops and I don't ever reach T. So that's a non-deterministic algorithm for figuring out whether S is connected to T in a graph. Okay? So we also wanted to figure out what was the hardest problem in NP, because NP isn't that far away from what we consider tractable in the real world, quote unquote. So we wanted to figure out what the hardest problem was in NP. So we figured out this notion of NP completeness. And NP completeness says for a problem B, so B must be in NP itself, because you can't be complete for something that you're not in. And B is NP hard. So what was that notion? That means that it's essentially it means the hardest problem in NP. And more formally, that means I can transform any problem that's in NP to this really hard problem. And so if B had an easy solution, an efficient solution, then everything else has an efficient solution because I can just transform it to B, which now I assume has an efficient solution. So this means that for all A in NP, so for all problems A in NP, A polynomially reduces to B. So I can transform an instance of A in polynomial time, so efficiently, into B. Okay? So that's what it means to be NP hard in NP, which implies NP completeness. And so we thought about this for a while and figured out there actually are some problems that are NP complete. So the first one that we found out was that we didn't prove, but we can reason why it is NP complete. It's called 3 satisfiability. So I'm given this 3 CNF formula. So I have ors of what are called literals, and ands of clauses which contain less than or equal to 3 literals. So literals can appear either in the positive or the negative form. And so we figured out the problem, which is 3 sat, is I'm given this 3 CNF formula, and I want to figure out, is there a way to set the literals, well really the variables, of the formula to make the formula evaluate the true eventually. And so that problem is NP complete by Cook and Levin in 71. So Cook and Levin in 1971. And so that was essentially the first NP complete problem that was proved, even though if you look at the original paper, they actually don't use 3 here, but and they actually don't even introduce this idea of NP completeness, but they it is NP complete by their work there. But we also came up with some other NP complete problems related to graphs. So we came up with Hamiltonian Path. We also came up with clique, and the brother problem or sister problem to that, independent set. So Hamiltonian paths is I'm given a graph and 2 vertices S to T, and I want to figure out if there's a way, if there's a path from S to T that visits every vertex exactly once, and no more than once, and not 0 times either. And that happens to be NP complete by either a reduction from clique or independent set or from 3 set. We did it from 3 set. And we also showed that clique and independent set are also NP complete. Clique is the problem, you're given this graph in an integer k, and I want to figure out if there's a complete subgraph of k or more vertices in this graph. Independent set is the opposite question, essentially. It is, I'm given this graph in an integer, and I want to figure out if there's a way to choose k vertices of the graph with no edges between any of those k vertices. So it's like the opposite of a clique. Okay? So we started making more and more problems. We also did the undirected version of Hamiltonian Path, so we also did that. But there are thousands and thousands of NP complete problems. We can spend our entire lives studying this. So, but I don't think that would be quite fruitful. So what I would think would be interesting is, let's look at viewing complexity in a different way. Let's try to reason about, are there problems that are harder than NP? Are there problems that are really within P? Are they really low complexity in a sense? And so That's what we're going to do essentially today. Although we did cover undecidability about some problems that we know don't have any algorithms to solve them. And some of the problems we talked about were the acceptance problem, which is I'm given a Python program, let's say, and some input to that program, and I want to figure out if that program will output true, for instance, on that input. And we showed that there's no algorithm to solve that at all. Or another problem is the same thing, a Python program and an input, and I want to figure out if it's going to halt on that input. Is it going to ever stop on that input? And of course, I could just run it on that input just to see, but it may run forever. But it turns out there's no way to algorithmically show that you can't do that. So what we're going to do today is we're going to basically go below undecidability, but above NP completeness. And also we're going to go below P also. See how far we can go below and how far above we can go also. So any questions about any of this that we've covered so far? Okay. So I'm going to make basically a really long line. So what this line will represent is complexity hardness in a sense. So the further right you get, you're getting into the more difficult problems. And the further left you get to the more easy quote-unquote problems. And so what we're going to do is we're going to put P and NP somewhat in the middle. So those are the classes we've been talking about. And we know that P is a subset of NP, right? Because NP, you're granted this nondeterminism, which will guess the correct answer if there is one. So it's more powerful, at least as powerful as just trying all possibilities, which is what P is essentially. So we know that P is a subset of NP, but we don't know if the other direction is true, which is that million-dollar question. So what we're going to do is we're going to start working on the upper end first. So what kind of measure are P and NP measuring essentially? So polynomial time, right? So what is another measure that we care about a lot? Space, right? So it might be nice to figure out where space fits on this chart, right? Is it over here? Certainly, if you have polynomial space, then you can, it's at least as powerful as polynomial time, right? Because in order to be able to even write that amount of space, you need that much time anyway. Because in polynomial space, you might get a lot more because you can reuse space. So what I'm going to define P space as, so P space. So this is Polyspace, unlimited time. Okay. So the only limit that I have here is that you must operate in a polynomial amount of space, but you're granted unlimited time, as much time as you want. Okay? So let's see. So you can actually observe that NP is a subset of P space because any NP problem, like 3-set, let's say, you can operate in polynomial space, right? Because what you can do is, let's just say we're looking at 3-set, and we can say that I'm going to try the first, I'm going to try all zeros on every single variable in the formula, and then I'll see what that is. If it's true, then I'm already set. If the formula evaluates it true, I'm already set. Then I throw away that set of zeros. I reuse that space again. Then I try 0, 0, 0, 0, 1. Then I try that one. Then I try the next one. Then I reuse the space, reuse the space, until I try all to the n possible settings to the variables. So I'm essentially reusing the space over and over and over again. And so that's essentially why NP is a subset of P space, because I can simulate an NP complete problem in polynomial space, right? And if you wanted, let's just say that you wanted to figure out, oh, Hamiltonian path, is that in p-space? Well, what I can do is, since it's NP-complete, I can reduce it to 3-set, and then just do the 3-set algorithm. Okay, that reusing space algorithm over and over. So that's why NP is a subset of p-space. And so you may want to figure out, well, we came up with some problems that are complete for NP. Are there such things for p-space, right? And there's a very famous problem called TQBF, which stands for totally quantified Boolean formula. And what that is basically a generalization of satisfiability. So what you have here is a set of quantifiers on the variables. So let's just say Q1, X1, Q2, X2, Qn, Xn, phi. So phi here is the formula. So the formula is of the same structure as 3-set with all the ands and ors. It doesn't have to be in conjunctive normal form, but you can if you want. So that's the formula. So what are these Q's? So Qi is either exists or for all. So how many of you are not familiar with these exists or for all? Okay, some of you. So essentially, what this means is that, let's just say that Q1 is exists. So exists means that there is some setting of x1 that I can choose, either 0 or 1. There is a choice that I can make to make phi true. There is some choice. But let's say that it was for all instead. In that case, every single choice that I can make for x1 has to make it true. And so what I have here essentially is this problem. You're given these quantifiers on the variables. So this one maybe exists, this one may be for all, etc. for all variables. And so what you want to figure out is there a way to make the formula true while following the criteria for all the quantifiers, right? 3-set essentially is there's a choice for x1, there's a choice for x2, up to xn, there is a choice. So there you have that exists for all the variables, right? There is a choice for x1, there's a choice for x2. But here, now I'm going to generalize it and say every single choice you have to be able to make the formula true with x1 if it was for all. Okay? So that problem is p-space complete. And p-space completeness is defined very similarly to NP completeness. You have to be in NP, and any problem in p-space has to polynomially reduce to TQBF, as this problem is called. So it's called TQBF. And by polynomially reduce, I mean polytime reduce. So it's the same kind of reductions as before for NP completeness. Okay? So all of these problems I'm going to talk about today, I'm not going to go very far in deep, but are there any questions so far? Yeah?
What would be in polytime instead of polyspace?
No, oh, this is p-space complete. It's polytime reducible from any p-space problem. So since I say it's complete, it must be in p-space and it must be p-space hard. And p-space hard means that any problem in p-space, I can polytime reduce to this problem. So it's complete for p-space itself.
So it's basically the same thing as P and NP.
With NP, yeah. The only difference is that NP is replaced with p-space. Okay? So any other questions? Okay. So some other really cool results is that we actually don't know, obviously, whether P is equal to NP or not. That's the $1 million question. And so you may be wondering whether if we, well, P-space is defined as deterministic polyspace, right? That's what it's defined as. What about non-deterministic polyspace? And that actually turns out to be a really interesting question. And we know that P-space is equal to NP space. So whether as here, we don't know whether P is equal to NP, we actually do know that P space is equal to NP space. And that's by Savage in 1970. So it's called Savage's theorem. He actually showed a more general result than this. So a problem solvable in non-deterministic f of n space can be solved in deterministic f of n squared space. So instead of, like for NP, we may have, because it's time, you may have an exponential growth in terms of how much time you use. With space, since you can reuse space, you only get a square factor here. So essentially, let's just say that we have a problem that runs in non-deterministic, let's just say n cubed space. By Savage's theorem, there's a deterministic O of n to the sixth space algorithm for the same problem. Okay? So think about it. If you have a non-deterministic polyspace algorithm, that means you run in space n to some constant k. Then by Savage, you can convert it to a deterministic O of n to the 2k space algorithm, which is still polynomial because it's n to some constant. It's larger constant, but it's still a constant. Okay? And the reasoning for this is that essentially because you can reuse space, you essentially can throw away half of the computation, what you've done so far, once you're done with it. So I won't get into what all the details are, but essentially that's the main idea. For P and NP, you couldn't reuse space, but for P space versus NP space, you could reuse space. So that's the essential idea. So if you want to look up Savage's theorem, it's actually a really cool result. Okay. So let's start going a little higher. So polynomial space. So what's the next thing beyond a polynomial? Exponential, right? So do you think the next one will be exponential time or exponential space? Time, right? Because it's clear that because of P space versus P, exponential space is at least as large as exponential time. So exponential time must be the next one, at least, yeah. So let's look at exponential time. So I'm going to call it exp time. So let's see. If we have a polyspace algorithm, does that mean that we can run in exponential time? Well, let's do the same strategy as we did with NP and 3-sat and showing that NP is contained in P space. So if we want to show P space is contained in X time, what we can do is we can show that we can run TQBF in exponential time. Exponential time, right? So what can I do? I could just try all 2 to the n possible choices of x1 through xn, subject to the quantifier constraints, right? So that's actually an easy way to show that P space is a subset of x time. Okay? What's that? Right, so, well, there are 2 options I can choose for x1, either 0 or 1. Obviously, there might not be all 2 to the n possible choices because for all basically limits you on that. You'd have to choose both of those, but I could just run all of them and then just figure it out. So it's essentially the same thing as 3-set before. But here I didn't have to throw away the previous computation. I can just run every single possible computation there and not have to throw away. I could if I wanted to, but I don't have to here. Any questions about that? Okay. So obviously we don't know whether P is a strict subset of NP yet. We don't know that. We actually don't know whether NP is a strict subset of P space either. And we don't know whether P space is a strict subset of X time either. So it's quite funny. Most people say that complexity theory is like a doom and gloom kind of field because it's full of these negative results. Like, we don't know whether this is true. We don't know if this is true. So it's quite sad in a lot of ways. But we actually do have a nice result here. So we don't know whether which one of these is strict. We actually believe that every single one is strict, but we don't know which ones exactly. But we do know at least one of them must be strict, because we can show that for P and X time, these are not equal. Okay? And that was due to, let's see if I can read my handwriting. This is due to Hardness, I guess, and Hardness in 65. It wasn't exactly showing P and X time because these notions weren't quite established at that point, but that's what they essentially showed. So what they were able to show was that there is a problem which can be computed in exponential time, but we know can't be computed in polynomial time, okay, which is actually quite striking. So that actually shows that if we look at exponential time complete problems, then we know they don't have polynomial time solutions, okay? And so an example of an x time complete problem is chess. Chess. So it's a generalized form of chess. So it's not just an 8x8 board. You have an n×n board, and then what you want to figure out is if the first player wins. So that's your decision. You have to figure out if there's a way for the first player to win, given a particular configuration of the board. And if there's no way to win, then you say no. So that turns out to be an exponential time complete problem. And so because it's exponential time complete, we know since these two are different, then there's no polynomial time algorithm for chess. Which is why a lot of companies like Google and other artificial intelligence companies are devoted to problems like chess or Go or things like that, basically making a computer player that performs extremely well, but we know they don't have efficient algorithms because of this separation between P and X time. Okay? And the result is commonly known as the time hierarchy theorem. So let's see. So this is called the time hierarchy theorem. And essentially what that is, space. I need polynomial space. So essentially what it is can solve a problem in O of f of n time, but not in. And so, does anyone know what little o is? So, you know what big O is, right? It's either equal up to a constant of this function or less, right?
Probably the opposite.
It's almost the opposite. Little o means strictly less than. It can't be equal up to a constant. There must be some separation. So this, I'm going to make this O bigger, but not in little o. of, it's not quite f of n, but f of n over log f of n. So that essentially shows that p is different from x time because anything that runs in 2 to the n time, if you divide by log, that's certainly more than a polynomial. So therefore we have a separation there. Okay? So now you're thinking, you filled up that half of the board pretty thoroughly. So now, what about this left half of the board? And so, let's think about this. What is less than a polynomial? Logarithm, right? And so, keeping with this trend, we have time here. So what do you think would fit next right under p? Something to do with log, but is it space or time? Yeah, it'd be space, right? Because if I thought of it as logarithmic time, then it would be even below logarithmic space. So the one right below polynomial time should be logarithmic space. And so we're going to talk about 2 different classes, which are the deterministic log space and non-deterministic log space. So those classes are called L and N. So L means you can solve it in logarithmic space in terms of the size of the input, and NL is non-deterministic log space in terms of the size of the input. Okay. So we know, obviously, that the deterministic version is a subset of the non-deterministic version, just as we did with NP and NP. And it's actually true of P space and NP space. Even though they're both equal, P space is definitely a subset of NP space because non-determinism definitely gives you more power. And it's actually open whether these are equal or not. We don't know whether L is equal to NL or not. And NL is a subset of P because of the same way that NP space is a subset of X time. You essentially just try all possibilities because 2 to the amount of space you use, well, you're given logarithmic space. So 2 to the log n, that's just n, right? So that's definitely a polynomial amount of time, just by enumerating all possible settings of the space. So now, since we've been talking about polynomial time reductions in NP, polynomial time reductions here, polynomial time reductions here, now we're below the point of having polytime reductions, right? Because we want reductions that aren't too powerful, that are more powerful than the class, right? Because if we did that, then we would be able to solve problems in here anyway. So I want to find another type of reduction here. So what we do here is logarithmic time reductions. So it's defined the same way as before, but for NL complete, we have a logarithmic space reduces to b. So instead of granting you polynomial time, I'm granting you logarithmic space in terms of the size of the input. There are a few other things you need to worry about, but essentially that's what you're trying to do. And so it turns out that there are NL complete problems. So one of them that you've actually kind of solved on your homework is 2-set. So I'll just write NL complete. So some of them are 2-set. So this formula with this 2CNF formula with 2 or fewer literals per clause. Now I want to figure out whether the formula is true or not. That turns out to be an NL complete problem. So even below P and below, it's below P, and it is NL complete. Another one is a directed path. So I call it dir path. So what is that? Dir path is you're given a graph and 2 vertices, S and T, and want to figure out if there's a directed path from S to T. So if there is a directed path from S to T, then I say yes. If there isn't, I say no. And it's easy to see that as an NL, right, for a dirt path, because I can just non-deterministically start from S and then non-deterministically choose vertices along the way, right? But the problem is that I'm only allowed logarithmic space, even though it's non-deterministic. I'm only granted logarithmic space here. So I can't store all the previous vertices that I've computed because that could be linear in the size of the graph, which I don't have enough space now. So what I can do is, since it's non-deterministic, if it has a way of saying yes, it will say yes, right? So what I can do is, I can non-deterministically choose a vertex from wherever I am, delete whatever I was at before, and then just keep going from where I ended up. So I basically only keep in memory one vertex at a time. So I have S in memory, then I pick whatever vertex I pick next, then throw away the information about S, then I pick the next vertex, throw away the information about the first vertex until I reach T, or I find that they aren't connected at all. Okay? And so that actually shows that undirected path is also an NL. Okay? So here, let's think about this. What do you think about P space and complement of P space? So if I just flip the yeses and nos, can I do that for a P space algorithm? Well, let's think about it. Nondeterministic is not really doing this, but essentially trying all possibilities at once. Don't quote me on that. It essentially is doing that, but it's not actually doing that. So the way that a P-space algorithm, a non-deterministic P-space algorithm would say yes is that if there is some way, this computation path, if there's some path that says yes, many others may say no, but if there's one that says yes, then I say yes, because there was some way to get to the yes answer. So if we just flip the yes and no answers on a non-deterministic algorithm, then some path may say yes, and another one would say no. But if I flip that, that's one path says yes now, and the other one says no. So because by flipping the answer, you still say yes on the input, even though you should say no. But if you have a deterministic one, you only have one computation path. So if you end up in a yes answer, if you flip it, then you say no. If you were in the no, you say yes. So it turns out that P space is equal to co-P space. So if I flip the yes and no answer, I still get polynomial space, and it is exactly the same class. We don't know whether, and obviously since P space equals NP space, then P space equals co-P space equals NP space equals co-NP space. So we know all four of those are equivalent. Obviously, since in the same manner for P as for P space, P is equal to co-P. So the only change here is that space is replaced with time, but since that is just changing yes to a no, that doesn't really matter. We don't know whether NP is equal to co-NP or not. And if they were equal, then all hell would break loose in the theory community. Like, classes would collapse to other classes. It'd be insane. So we know P space equals co-P space, so these four are the same. We don't know if these four are the same, and we don't know whether these two are the same. But we know that NL equals co-NL. So I like talking about these kind of results because you have three different possibilities. Either you have everything is the exact same class, you have possibly some separation, and here you have some partial separation. So you have some equality, but possibly we believe that these are different. We don't know if they really are them. And this result is due to, and please forgive me for the names because I cannot pronounce them. So Emmerman in 88, and I'm not even going to try this one. And use Y. Whoever this guy is in 87. So what they were able to show is that we have these NL complete problems. So if I show that any of them are in co-NL, then if they are in co-NL, then they're also complete for co-NL, right? So therefore, if I show any of these are in co-NL, then I show that both of these are the same. And that works also for NP and co-NP. If I show any NP complete problem is in co-NP, then I show that those two are the same. Because I can just reduce to the now co-NP complete problem. So what they did here is just essentially show that der path is in co-NL. And so essentially that means the NL problem is, given a graph of two vertices, I want to figure out if S is connected to T. In the co-NL version, I want to figure out if S is not connected to T. And that might be quite difficult, right? Because I can't store too much information here because I only have logarithmic space. But the non-determinism really helps there. Okay. What are we doing on time? All right, so I'll do a little bit more. So we have this time hierarchy theorem, which says that P is different from X time. The classes L, NL, not NP, but P space, all of those relate to space. So you may think, maybe there's a space hierarchy theorem, and it turns out there is. And so I could not find the original authors for this, but the space hierarchy theorem, that says that if you can, I'll just say it this way, some problem can be solved in big O f of n space, but not in little o f of n space. So what that boils down to is there's some problem I can solve in big O n squared time, but I can't solve it in n to the 1.99999 as many nines as you want space. So even the smallest change in the amount of space could vastly determine which problems you're talking about. So from this space hierarchy theorem, it doesn't say anything about determinism versus non-determinism. So this doesn't resolve NL versus NL. But what this does show is that since L is logarithmic and P space is polynomial, take anything away from a polynomial, then you get fewer languages, fewer problems. So this shows that P space and L are different. Actually, this is even stronger because this also works for NL and NP space. So I can even strengthen this to saying that NL is different from P space. So I know that one of these three containments is true, and one of these three containments is true. We believe all of them to be true, but we don't know for sure. Okay. Any questions about that? So I just want to mention one more problem, and then we'll quit for today. So you may think here is directed path, and it's NL complete. So I can solve it in non-deterministic log space. And since we don't know whether L and NL are the same, we don't know whether NL can be solved in deterministic logarithmic space. We know it's non-deterministic for sure, but we don't know about deterministic. And so you may think, well, you mentioned that directed path is in there, and you said undirected path is also in there because it's essentially the same thing as directed path. But is undirected path NL complete? And we actually don't know that either, because it's actually shown that undirected path is an L. Right? So if we actually show that undirected path is NL complete, then that would show that L and NL are the same. Because if it's NL complete, then everything can be reduced to this L problem. But that means that anything can be reduced to L, even in NL, so therefore those two are the same. And so this was due to, it was actually pretty recent, around a decade ago, due to Reingold. So Reingold in 2004. It was actually pretty striking. Some of the theory is really nice there about what are called expander graphs and things like that. But it's pretty interesting how they were able to come up with that. And if we actually expand this out a little further to the right, we can show that if we look at X space, clearly exponential time is contained in exponential space. That's just because anything time-related is contained within the space-related thing. But by the space hierarchy theorem, we also get that because X space is much larger than polynomial space, we get that P space is also different from exponential space. So it's actually kind of like a spectator sport. Like you see all of these things that have to be true, that there are inequalities all over the place, but you're just sitting there wondering like which one's gonna fall next and things like that. So like, is this one gonna fall? Is this one gonna fall? So we know one of these two must be true. We know one of those three must be true, and one of those three must be true. But we don't know which one adjacent to each other is true. And a really interesting thing is that there are hundreds, literally, of classes in between each one of these that people study on a regular basis. So I think tomorrow I'll talk about a few of those just to spark some interest in like circuit design they're related to, or parallel algorithms. Some of those things are quite interesting. So are there any questions about any of this? So this is an absolutely rich field. Hundreds of papers published a year about problems that are reduced to lower complexities. Some problems that are shown to be complete in some sense. So this year it was shown that a generalized version of Mario Brothers is p-space complete. Whereas before it was shown to be NP-hard, so they actually resolved it to be p-space complete. A lot of two-player games, especially like in artificial intelligence, are shown to be p-space complete, although some are X-time complete. Not many classes are shown to be NL complete recently, but there are a lot more problems that are shown to be some kind of completeness. And you can even go higher than this by going to, say, doubly exponential time, doubly exponential space, or even higher than that. And you can also get these separation results there. I think that's enough for today. So are there any questions about any of this? Any questions about assignments, projects, any of that? All right, I'll see you tomorrow.